Jai Jagannath. Today is the lecture 2 of Gauss law. So you see, in the last class I was discussing about the flux. Okay, suppose you see, you take an example. Let us say this is x, this is y, this is your z axis. So now you take a cylinder. Let us say either it is a closed cylinder or solid cylinder. So here there are two surfaces. One is this surface. This is second surface. Let us say this surface area is A. This surface area is also A. So this is our first surface. This is second surface. And this curved surface is your third surface. Okay. So this curved surface is your third surface. So now we will find, let us say, the electric field. Electric field is along the direction of what? Along the direction of x-axis. So if electric field is along the x-axis and this cylinder is lying in which plane? Y and Z plane. Suppose you see, this is my cylinder and this cylinder is in which plane? Y and Z plane. And the electric field is along which direction? X-axis. So we will find what is the total flux coming from this closed cylinder. So you know what is the formula of flux? Formula of flux is equal to phi is equal to surface integral of E dot dA. This is the formula. So now there are three surfaces. First surface, second surface, that is top and bottom of the cylinder, and the curved surface, that is your third surface. Okay. So now we will find what is the total flux. So total flux through the whole cylinder is nothing but flux due to first surface plus flux due to second surface plus flux due to third surface. Third surface is curved surface. Third surface is which surface? Curved surface. So that is equal to, if we will apply the Coulomb's law, you see here, Gauss law. So here you see, here electric field is uniform. Electric field is constant throughout this space. So here I want to find the flux to the first surface. So what I will do? So I will take the, since electric field is constant, so here area vector is away from the surface and electric field vector is towards the right. So what is the angle? What is the angle between this area vector and electric field? 180 degree. So here we can say the flux to the first surface is nothing but E dot area vector plus, here for second surface electric field is towards right and area vector is also towards right, because area vector is always away from the surface. So here the flux due in the second surface is equal to what? E dot A2 plus. So you see, if I will take a small element in the surface, closed surface of cylinder, so here area vector is away from the surface and normal to the surface, and electric field is towards right. So what is the angle between this? 90 degree. So I can write E dot A3. So that implied, so here in the first surface electric field is towards right, area vector is towards left. So I can write it is a dot product of E and A1 is equal to E A1 cos 180 degree plus for second surface E and A both are in same direction. So I can write E A2 cos 0 plus in the third surface the electric field is E and area is, let us say, A3 into cos 90 degree. So here that is equal to minus EA1 plus EA2 and this is cos 90 is equal to 0, but I have taken A1 is equal to A2. So if A1 is equal to A2, then total flux A1 is equal to A2 is equal to SA. That implies total flux is equal to minus E into A1 is nothing but A plus E into A2 is also A. So that will come 0. So what is the conclusion? The total flux is equal to 0 in this problem, particularly without charge inside the cylinder. Without charge inside the cylinder. So there is no charge inside the cylinder and there is an external electric field. So due to this, total flux through the surface is equal to 0. So we will discuss the Gauss law. So this is the statement of Gauss law. So what is Gauss law? Gauss law states that the total electric flux through any closed surface, that is a surface enclosing a definite volume, is proportional to the total electric charge inside the surface. Suppose you take a charge, this is plus q charge, okay, and so surrounding to this plus q charge you take a radius r and draw a sphere. So this is your which sphere? Imaginary sphere. Actually there is no sphere, so we are taking an imaginary sphere. So this imaginary sphere is called Gauss surface. So why it is called Gauss surface? Because we are applying the Gauss law to this imaginary surface. So this charge is at the center. So I am taking radius r. So now we will find what is the electric flux through this surface, closed surface. So now see the according to the mathematical analysis, the flux. So you can say this is your proof. The total flux is equal to which flux? Electric flux is equal to surface integral of E dot dA. This is the mathematical expression of the flux. And according to the Gauss law, this total electric flux from a closed surface is equal to total charge enclosed by this Gaussian sphere divided by epsilon naught. So what is Q enclosed? So it is the total charge within this Gaussian surface or within the Gaussian sphere. So now we will prove this. Now see, to apply the Gauss law, we have to take a symmetrical surface which is equidistant from this charge. So that means you take a small element on this surface. Okay. So this small element area is dA. And you know the area vector is always perpendicular to the surface. So this is your area vector of this small element. And you know for a sphere the area vector always lie along the radial line and it is outward. And what is the electric field intensity at this point? If you will keep a unit positive test charge, then this plus q will repel this plus 1 charge along this direction. So this is the direction of the electric field. So now we will find what is the flux through this small surface. So flux through the small surface of area dA is equal to, since the element is very small, so flux passing through that element is also very small, that is say d phi, and E stands for electric flux, is equal to, according to the formula, E dot dA. So here you see electric field and area vector both are in same direction. So E dA cos 0, which is equal to E dA. Now you know what is electric field intensity at any point due to a point charge which is at r distance from it. So you know that formula is Q by 4 pi epsilon naught r square. So here Q, this is the point on the surface, electric field is equal to this into dA. So this is what? Electric flux through the small element. But I want to find the total flux through the whole Gaussian surface. So the total flux can be written as phi e, which is equal to surface integral of d phi e, which is equal to surface integral of q by 4 pi epsilon naught r square into dA. So now q is constant, 4 pi epsilon naught is constant, and when you are integrating over the whole surface, the every element of the surface is at same distance r from the center. That means r is also constant. So you have to integrate only dA. So that implied q by 4 pi epsilon naught r square. What is the integration of dA? It is total area. So that implied the electric flux through this whole surface is equal to q by 4 pi epsilon naught r square into area. What is the surface area of a sphere? 4 pi r square. So 4 pi r square cancel. You will get q divided by epsilon naught. So this is the flux due to a point charge at any point, and we are finding the total flux through this whole Gaussian surface, whole imaginary surface, whole closed surface having some definite volume is equal to q by epsilon naught. What is q? Q is the charge enclosed by this Gaussian sphere. So I can write it is q enclosure, the total charge enclosed by the sphere divided by epsilon naught. One interesting point is that the flux does not depend upon the point, that is distance from the charge to that point. So here we can say flux is independent. Flux is independent of radius. Okay, so this is the proof of Gauss law. So let us take, suppose this is a charge particle q. I want to find what is the flux through the closed surface sphere of radius r1, and taking some radius r2, you draw another sphere. So this is your first surface, this is your second surface. You take another sphere of radius r3, and this is a third sphere. So if I will find what is the flux to the first surface, your answer according to Gauss law is equal to charge enclosed by this sphere, that is q divided by epsilon naught. If I want to find flux to the second surface, so that is also the total charge enclosed by the sphere, that is q divided by epsilon naught. So flux to the third surface is also q by epsilon naught. So that means flux does not depend upon the radius, or you can say the flux does not depend upon the surface. Flux does not depend upon the radius, or we can say flux does not depend upon the shape or shape of the sphere. Shape of the sphere. It does not depend. So now, so this is, I have taken plus q. So if I will take a negative charge and I want to find the electric flux through a closed surface of radius r. So here what is the value of flux? So here you see, since it is negative charge, the electric field is towards the center. And if I will take a small element, that is dA, its area vector is dA. So here the flux through the surface is equal to surface integral of what? E dot dA. So that is equal to E is towards center, dA vector is along the radial line outward direction. So theta is equal to what? 180 degree. So here it is E dA cos 180 degree. So you know cos 180 minus 1, that is E is equal to q by 4 pi epsilon naught r square into dA. So if you will integrate this, minus q by 4 pi epsilon naught r square comes out, and integration of dA is equal to area. So what is area? 4 pi r square. So you will get minus q by epsilon naught. So if the charge is negative, the electric flux is towards the surface. That means lines of force will be towards the surface. In case of positive charge, lines of force or flux is away from the charge. So I can write flux, electric flux is away from a positive charge, and electric flux is towards to a negative charge. So this is about the flux for positive charge and negative charge. See, for external charge, what is the contribution of towards the flux? For external charge, what is the flux through the surface? Now see, suppose this is a closed surface. This is a closed surface. Okay, so I want to find the flux through a flux due to external charge. Suppose this is the closed surface, this is the closed sphere or any shape, closed surface with some volume, that is 3D surface. So here this is an external charge. So now due to this external charge, what is the lines of force? This is the lines of force. This is the lines of force. So here, though electric field is there inside the sphere, but you see in this side lines of force entering. So here at this point, these lines of force is entering. At this point, these lines of force is leaving. So if lines of force entering is taken to be positive, lines of force leaving from the surface is taken to be negative. So that net lines of force is equal to 0. Here also, this is the lines of force entering to the surface. Here lines of force leaving the surface. So net lines of force is equal to what? 0. So here also same thing. So that means though electric field is there, but the same lines of force entering is equal to same lines of force leaving. So we can say net flux is equal to 0 due to which charge? Due to external charge. So that's why the Gauss law proved that the total flux through a closed surface is equal to surface integral of electric field, which is mathematical expression of the flux, but Gauss proved that the total flux is equal to charge enclosed by the surface divided by epsilon naught. Suppose you see, there are two charges, Q1 and Q2 in this closed surface. So this is 3D surface, closed surface, that is 3D surface. And there are external charge Q3 and Q4. So according to the Gauss law, suppose this is your positive charge and this is your negative charge. So now the total flux according to the Gauss law is equal to total charge enclosed by the sphere, that is Q1 plus minus Q2 divided by epsilon naught. Q3 and Q4 are the external charge which has no contribution towards the flux for this surface. So if you will prove, you can prove also. You see, Q3 is external. Let us take Q3 is external. You take the area vector dA here. Just opposite to this, you take same area vector dA. So here area vector is outward, and here area vector is also outward. But here this is charge. Let us say it is positive. So due to this positive charge, electric field intensity is away from it. So this is your E vector. And this is positive charge. Electric field at this point is also E vector. So definitely, if you will take a small sphere and this point is very close to this point, then electric field is assumed to be constant. Then what is the flux through this flux by Q3 on this surface? So you see, let us say here flux is equal to what? E dot dA plus here flux is equal to E dot dA It is a flux due to which charge? Flux due to Q3 charge. But here E and dA are 180 degree. So I can say E dA cos 180 degree, that is -1. Plus here E and dA both are in same direction. So flux is equal to E dA cos 0, that is +1. So total flux is equal to 0. So for external charge there is no contribution of the flux. So the flux is only due to which charge? The total enclosed charge, that is net charge. So this is your Gauss law. Another important thing is that, you see, suppose I will take this is a cone. Okay, this is a sphere, this is a cylinder, let us say this is a cubical cubed. So here inside this cone I am taking Q charge, and this is also sphere, I am putting same Q charge. Here inside the cylinder I am putting same charge Q, here also Q charge. So if anybody will ask what is the flux through this cone surface, you will write flux is equal to what is the charge enclosed by this cone? Q by epsilon naught. Here flux through the sphere is also Q by epsilon naught. Here flux through the cylinder is also Q by epsilon naught. So here flux through the cubed is also phi is equal to Q by epsilon naught. So that means so long as charge enclosed by the surface is remain constant, then flux everywhere remains constant. So what is the conclusion? Conclusion is that flux does not depend upon shape of closed surface, so long as charge remains fixed, charge remains same. So long as charge remains same, flux does not depend upon shape of the body. So in the previous before that I had also told flux does not depend on size of body. So I had taken for small sphere flux is the same, plus bigger sphere flux is same. So flux does not depend upon size of body, and flux does not depend upon shape of the body. So let us discuss test your understanding 22.3 of University Physics book. So in this figure 6 point charges are given and all lie in same plane. They are lying in the same plane. So 5 Gaussian surface, that is S1, this is S1 surface, this is red color is S2 surface, and this is your S3 closed surface, this is S4 closed surface, and this is S5 closed surface. 5 surfaces are there, and you have to rank these 5 surfaces in order of the electric flux through them from most positive to most negative. That means in every surface you have to find the flux. So what we'll do? You see, the first we'll find what is the flux to the first surface. You see, the first surface means S1. Within S1 there is no charge. Surrounding to S1 there are charges, but these charges are external for this S1 surface, and charge enclosed by this S1 surface is 0. So we know flux is equal to Q enclosure divided by epsilon naught. So here inside the S1 there is no charge, so flux through the first surface is equal to 0. Then come to flux through the second surface. So this is your second surface. In the second surface, within red color, you see there are 3 point charge, -7 microcoulomb, 9 microcoulomb, plus 5 microcoulomb. So what is the total flux through this S2 surface? So we know flux through the S2 surface is equal to total charge enclosure within the Gaussian surface divided by epsilon naught. That is net charge. So in this S2 surface, first charge is 5 microcoulomb, plus second charge is -7 microcoulomb, plus third charge is 9 microcoulomb divided by epsilon naught. 9 5 14 minus 7, that is equal to 5 2 is equal to plus 7 microcoulomb divided by epsilon naught. So this is your phi 1, this is your phi 2. Now come to flux through the third surface. You see third surface, this is a third surface. In the third surface, the total flux is equal to net charge by epsilon naught. So what is the net charge? 9 plus 1 microcoulomb plus minus 10 microcoulomb divided by epsilon naught, that is equal to 0. So this is the flux to the third surface. Come to flux to the fourth surface. You see, this is your fourth surface. In the fourth surface, there are only two charges, 8 microcoulomb and minus 7 microcoulomb. So what is the flux? Net charge divided by epsilon naught. So net charge is 8 plus minus 7 divided by epsilon naught, that is 1 microcoulomb divided by epsilon naught. So this is your phi 4. Then what is the flux through the fifth surface, last close, the outer surface? So within outer surface, what are the various charges? So 1, 2, 3, 4, 5, 6 charges are there. So just add all the charges. So the total flux is equal to 8 plus minus 7. So here 9 plus 1 plus minus 10 plus 5 microcoulomb divided by epsilon naught. So that is equal to 1, 9, 10, 11, 1, 5. So 6 by epsilon naught. So this is your phi 5. So what is our question? We have to rank these 5 from most positive to most negative. So you see, most positive is which one? Most positive, most positive. So this is your 6. No, 7. So you see, this is 1, this is second, this is third, and this is your fourth, this is fifth. So which is most positive? Most positive, most positive. That is second bit. Is it correct or something there is wrong? No. Yes. So this is first, second surface is the most positive. Then fifth surface. Then your fourth surface 1. Then S1 is 0. Then S3 is also 0. S1 and S3 both are 0. So this is the order. Now see, let us discuss example 22.4. So here what happens? There is an electric dipole, minus Q plus Q. Okay. So here this plus Q is lying within A surface, minus Q is lying within B surface. So there are 4 other surfaces. This C is a third closed surface and this D is a fourth closed surface. So you have to find the electric flux through each of the closed surface, that is A, B, C and D. Okay. So before discussing this line, whatever I have written already, so first you find out what is the flux through the A surface. So this A, within A, what is the charge enclosed? That is plus Q. So according to Gauss law, the phi A is equal to Q by epsilon naught. Then what is the, so you can write phi, this is electric flux for which surface? For A surface is equal to Q by epsilon naught. Then we will find electric flux from the B surface. So within this B closed surface, there is only one charge, that is minus Q. So according to Gauss law, the net charge divided by epsilon naught. Net charge is nothing but minus Q divided by epsilon naught. Then we will find what is the flux through the C. What is the electric flux? Through which surface? C surface. So within this C closed surface, there are two charges inside this C surface, minus Q and plus Q. So according to the Gauss law, the net charge is equal to minus Q plus Q divided by epsilon naught. So which is equal to 0. So net flux within the whole C surface is equal to 0. Then what is flux through D surface? Flux through D surface. In the D surface, there is no charge inside this D surface. So what is the total enclosed charge? 0. So the total flux through the D surface is 0. So this is a mathematical expression using Gauss law, and from the fundamental concept you see, in a sphere, in the A surface there is only positive charge plus Q, so electric field is always away from the positive charge body. So these are the lines of force. This red color indicates the lines of force which is coming out from this surface. So that's why the electric flux is outward. Okay, and what is that flux? Plus Q by epsilon naught. For B surface, since it is negative charge, so you know lines of force is always towards a negatively charged body. So here flux is equal to negative. And in the C surface, you see this line, this line, this line, these are leaving from the C surface, and just symmetrically you see these lines of force, these lines of force, these lines of force are entering. If lines of force entering is taken to be negative, lines of force leaving from the surface is taken to be positive, so these three are positive, these three are negative, just add, you will get 0. Similarly here lines of force will start from positive and end on negative. Lines of force start from positive, end on negative. So if we compare, you see from the C surface, this is the lines of force leaving from the C surface, this is the lines of force entering to the surface. So these lines of force will be cancelled, so net flux is equal to 0. Similarly here lines of force, this is positive charge, so lines of force are leaving, and this is negative charge, lines of force are tending to the negative charge. So for this C surface, these lines of force is away from the surface, these lines of force is entering to the surface, so net lines of force or net flux will be 0. So that implies the C surface, in the C surface, the total number of lines of force leaving is equal to total number of lines of force entering, so net flux is equal to 0. That is according to the concept. But according to the mathematical formula using Gauss law, we can say flux is equal to 0. Similarly, this is also D surface. This is also D surface. So here this flux is entering to the D surface. This flux by lines of force is leaving. So here this is positive, this is negative. So total lines of force is equal to 0. So here this is the lines of force entering to D, and this is the lines of force leaving from the D. So net lines of force or net flux is equal to 0 in this D surface. Now we will start application of Gauss law. So Gauss law is applied to find electric field intensity or flux at any point due to a charged conductor. So that conductor may be spherical, may be cylindrical, may be linear conductor. So we will apply. Before applying the Gauss law, there are 4 points we have to keep it in mind. So first point is that Gaussian surface. What is Gaussian surface? Gaussian surface is that surface on which Gauss law is applied. So that is an imaginary surface that should be symmetric about the charge or charge distribution. So let us say, suppose there is a point charge. Okay. So I have to find the electric field intensity at A point using which law? Gauss law. So what we will do? We will take a Gaussian surface, that is imaginary surface. So that surface must be symmetric about the charge or charge distribution. So you see, if I will take and suppose the distance between this charge and this point A is r. So what I will do? I will draw an imaginary sphere, not circle. This is not circle. So this is imaginary sphere. So this surface is called Gaussian surface, on which we will apply Gauss law. Clear? So this is the closed surface. This is the closed surface, and our Gaussian surface is nothing but a sphere, imaginary sphere. So that sphere is passing through the point A, where we have to find the electric field intensity. So first point is, I think it is clear. So first we have to take a Gaussian sphere, which must be symmetric about the charge or charge distribution. What is charge distribution? You see, suppose I will take a linear charge conductor. Let us say this is positive charge. The total positive charge is uniformly distributed over this infinite conductor. So I want to find the electric field intensity at this A point. So what I will do? I will take a symmetrical Gaussian surface. So for that I have to take an imaginary cylinder. So this is your imaginary cylinder which is passing through the point A. So this imaginary cylinder is our Gaussian surface. Okay. So why I took this cylinder as the Gaussian surface? Because you see, this is the linear charge distributed conductor. If I take every point, this point, so this point is at r distance from this charge conductor. If I take this area, this small element, so that is also r distance from this charge conductor. If I take here, if I take another point here, this point is at same r distance from this linear charge conductor. So this is the Gaussian surface. Now here you see, if I take a point, I want to find electric field intensity at this point. So this point is also at same r distance from this charge. So this is the first point. I think it is clear. Second point, electric field must be same or symmetric at all points on the Gaussian surface. Now see, here on the Gaussian surface I have taken A point, B point. So here what is the electric field intensity at A due to point charge Q? So that is Q by KQ by R square. So here what is the electric field intensity at B? Same formula, KQ by R square, because R is fixed, R is same. For every point is at same distance r, so that electric field intensity is symmetric. Similarly here, if I will take this point, so here this is positive charge. If it is infinite conductor, we can say the electric field is normal. So here if I will take another point, the electric field, same electric field, so same electric field strength will get every point on the surface. So we have to choose the symmetrical surface as Gaussian surface. Next, angle between electric field and the area vector must be same at every small element area on the surface. So you see here area vector, if I take a small element on this surface of the Gaussian sphere, the area vector is equal to what? Area vector is always outward. So here angle between area vector and electric field is 0. If I take the small element here, then area vector is equal to this. Electric field vector is also same. So here angle between E and A is same. If I take a small element here, then the area vector is equal to outward. Electric field is also outward. So angle is 0 degree. Similarly, here if I will take a small element, then what is the area vector? Area vector is away. And from this positive charge, how will get the electric field? So if I will keep a plus 1 here, this positive will repel this plus 1 along this direction. So this is the direction of electric field. So here angle between E and A, angle between here A and E and A, angle between E and area vector here, everywhere it is same. Fourth point, Gaussian surface must not pass through any point charge. Suppose this is the point charge I have taken. For this point charge, we have to take the electric field or flux through the surface. So here this Gaussian surface is not passing through this charge. Or you can say here this is the charge distribution. So we have taken the Gaussian surface which is not passing through this charged body. So in this way, to apply the Gauss law, we have to keep these 4 points in mind. Now let us discuss this problem. We will apply Gauss law to find electric flux from this cylinder. So what is the electric flux from the cylinder? If a charge of 5 coulomb, is placed on the top surface of the cylinder. Now see, so this charge is lying on the top surface of the cylinder. But to apply the Gauss law, we have to take a closed surface. So what we'll do, you just take an cylinder, imaginary cylinder of same length L. This is the length of the original cylinder. we are taking an imaginary cylinder of length L just above this cylinder. So now you see, let us say this is E and F. Now this EBAF is closed cylinder, where Q is the charge enclosed. Q is the charge enclosed by the whole cylinder, that is ABEF cylinder. Okay, ABEF cylinder. We have to find what is the flux due to this ABCD cylinder. Now see, we will apply Gauss law. So what is Gauss law? So according to the Gauss law, the total flux coming out from the whole Gaussian surface, here Gaussian surface is nothing but Gaussian cylinder, is equal to charge enclosed by the cylinder, that is Q, divided by epsilon naught. So this is the flux, total flux coming out of the whole cylinder, that is Q by epsilon naught. But we are interested to find the flux through which cylinder? ABCD. Flux through ABCD cylinder. So this is just half of the total cylinder. So the total flux from this AB cylinder will be total flux divided by 2, that is equal to Q by 2 epsilon naught. So this is the answer. So here if charge value is given 5 coulomb, just put 5 divided by 2. Epsilon naught is at nothing but 8.854 10 to the minus 12. So just you calculate this. If you calculate, you will get the flux. So what is the unit of flux? It is Newton per coulomb into meter square. That is phi is equal to E dot A. So this is the answer. Now let us discuss this question. A charge Q is placed. This Q is a charge which is placed at A by 2 height from the bottom surface of a cube whose side is A. Question is, you have to find the flux through this surface. That means, what is the flux through this bottom surface? What is the flux through the bottom surface? Let us say this is ABCD surface. So we have to find the flux. We have to find the flux through the bottom surface, that is ABCD surface, is how much? Now what we'll do, so since this is a cube whose side is A, then total flux from the whole cubical surface is equal to, according to Gauss law, it is total charge enclosed by epsilon naught. So here within this cube, what is the charge enclosed? This is the value of Q divided by epsilon naught. So this is the total flux which is equal to Q by epsilon naught from how many surface? From 6 surface, because in a cube 1, 2, 3, 4, 5, 6. So there are 6 surfaces. Okay, 6 surface where each surface is a square. Okay, so from 6 surface the total flux coming out is Q by epsilon naught. But our question is, you have to find flux through only A, B, C, D surface. So that is one surface. So flux from one surface is equal to, the total flux is equal to Q by epsilon naught divided by 6 surface. So this is the flux from any one surface. So now see, find flux through hemisphere if a charge of Q is placed, at C point, that is on center of top circular surface. You see, let us say this is a hemisphere. You know a hemisphere? Just you take a sphere just like a cricket ball, just symmetrically cut in the center, so you will get a hemisphere. In the hemisphere, at this top surface, that is circular surface, at the center there is a charge Q. So we have to find what is the flux through the hemisphere. So now you see this charge is lying on the top surface. It is not lying within the closed surface. So what we'll do? We will use Gauss law. So to find Gauss law, we have to take a Gaussian sphere. Gaussian surface. Okay, so to make it a closed surface. So what I'll do, I will take an imaginary hemisphere above this hemisphere of same radius. Suppose the radius is r. Suppose the radius of this hemisphere is r. So with same radius, I will take another hemisphere just on the top of this bottom hemisphere, so that the total will be a closed surface, Gaussian surface. So which is a sphere. Now first find out what is the flux, total flux from the whole Gaussian sphere. So this is called Gaussian sphere. Gaussian surface, our surface is a sphere, so we can say it is Gaussian sphere. So the total flux from the Gaussian sphere is equal to charge enclosed. What is the charge enclosed within this sphere? Q divided by epsilon naught. So this is the total flux to the whole sphere. So question is, what is the flux to the hemisphere? So hemisphere is the half of the sphere. So total flux from the hemisphere is equal to total flux divided by 2, that is Q by 2 epsilon naught. Okay, so this is very small application of Gauss law. So in the coming class we will discuss some other application. Okay, bye.